Loud enough? Good. All right, welcome to the Department of Physics and Astronomy. I'm an associate head, and now is the official start of the 2019 Physics and Engineering Festival. Yay! So today we are happy to welcome Dr. Jérémie Palacci, who is going to present Science of Beer. And Professor Palacci came from University of San Diego, University of California, San Diego. Oh, what have I almost done? University of San Diego is a different university. Yeah, and his research interest is actually soft matter, or as he calls it, science of squishy things. Because obviously he came from France, where he was exposed from early age to things like cheese, croissants, mayonnaise. And, but since he moved to San Diego in 2015, right? He found out that San Diego has 123 breweries, maybe even more. So naturally he developed the second research interest, science of beer. And today he will report his beer-inspired observations to us. And he will be also joined by the local beer expert and practitioner, Dean Brundage. And I believe they will continue from that point. And okay, let's give them a round of applause.
Thanks, Alexei. And it's a pleasure for us to be here to kick off the Texas A&M Science Festival this year. So Dean was a partner at New Republic Brewery until a couple years ago, and is the expert in brewing beer. My role in this presentation would be to tell you about like fun facts in science around beer. And so, Dean, can you tell us a bit more about you?
I'm going to be talking about the fun stuff about beer. I started New Republic in 2010 and exited in 2016. Went over to a place called Blake Steaks, where I run the beer and eat cheesesteaks.
Thank you. And one thing I wanted to stress is like this work was made in collaboration with two breweries, Mike Hess Brewery in San Diego, and we exchanged also with Blackwater Draw here in College Station, and Dean is a good friend of the owners of Blackwater Draw, and was nice enough to come share all his knowledge with us.
Chris called me up on Wednesday night and said, hey, I got a thing on Friday, I can't make it, so can you come? So here I am.
Okay, shall we start?
Let's do this.
Okay, so just like a quick recap on beer in the US. So those are data from a couple years ago. So there's 6.6 billion gallons per year, so it's roughly 28 gallons per person. So it's 100 liter, if you speak liter rather than gallon, per legal adult. If you think about it, it's 1 pint every 3 days. That's a fair amount.
Seems a little low.
And and here you can see just like the number of breweries in the country. You can see there's a few anomalous points like here, where it seems that a lot of breweries, it's actually very few people. That's where it's coming from. It's a division by 0. And one interesting fact is that the number of breweries in the US is finally about to reach the highest point that was 150 years ago. So the largest number of breweries there was in the US was in 1873, and there were 4,131 breweries. And we are finally getting back to that point. You could argue that transportation was different at that time, and so maybe people consume a lot more now than back then. But it took 150 years to make up for the maximum.
And that number from 2015 is, of course, out of date. We're around 6,000 now.
So the story tonight is a story about beer. And what is striking about beer is that it's actually only made of 4 elements, which is barley, hop, water, yeast. So it's like fairly simple number and list of ingredients, and still you can make so many different beers. And so tonight we'll try to explain you where the magic come from, where the science come from, and what is the intersection between the two.
Yeah.
So it all starts with the harvest. You go to the field, you get the barley, and then you take this barley and you put it in water, okay? And so that's the barley, that's what it looks like. And here at the top of the barley, like this part, there's a tiny hole. It's called the micropyle. And when you put the water is going to migrate inside the barley, inside the micropyle, and it's going to kick off the birth of the embryo. And the embryo, while becoming alive, is going to start to trigger the growth of an hormone. And this hormone is going to start like chewing up, making its way out, and generating the synthesis of an enzyme. Okay? And this enzyme is going to start like chewing up the walls and the walls of the starch reserve. Okay? Because the whole point and the whole story we're going to tell you tonight is how you can take this barley and make the sugar inside accessible so that the yeast can turn this sugar into alcohol. Okay? And that's what we will tell you tonight. So there's one trick to it. So you put your barley, you put it in water, and then like your enzyme starts developing and chewing up the walls. But then, if you wait too long, what happens? I mean, your embryo is meant to become a plant, and then it just becomes a plant. And for a brewer, it's terrible, because it means that you wasted sugar.
It is.
You wasted sugar to make a plant. And as you want your sugar to become alcohol, you want to make sure that as little of it is lost. So you never want to make this happen. This is bad. So this is typically after 5 days. So the first step takes a few days, and then you make sure that there is no springing of any plants, and you get your barley this way. So here I'm going to make a small tangent about like proteins. Do you know what a protein is? So a protein is a big like biomolecule. Okay? And so the way a protein is made is you have your DNA, and your DNA is transcripted into your RNA, and then it gets into this blue machine, which is a ribosome. Okay? Forget about the technical term. Basically, this RNA, like each gene, is kind of a barcode, which is telling you what little pearl you want to put, what color. There's only 4 types of pearls, and this guy is going to tell you, put a blue pearl, put a red pearl, put a yellow pearl, and so forth. Okay? So the ribosome is just like reading it and assembling like this long chain. This chain is a protein. So there's one trick to it, which is the ribosome is making like this very long string of pearls, but it's a 1D thing. Okay? And in order to be functional, a protein has to fold in 3D. And so you have this rope that you want to fold in a structure. And the structure can be very complex. And somehow, it works. And you can get something as complicated as that. And I say somehow it works because it's really one of the most complicated problems of physics, and people have no clear idea of how it works. But you have this really complicated this really long 1D sequence, which turns into this very elaborated 3D structure. And it's essential, because if it doesn't fold right, you have major disease appearing. For example, Alzheimer or Parkinson are all related to the fact that this 1D line didn't fold quite right. So it's very important. So I told you before that when you put the water, you would get like an enzyme popping up and starting like to chew up the walls. So the enzyme we're going to play with for the rest of this presentation and this story about beer is amylase. Okay? So it has 496 amino acids. And there's one thing which is very important when you have a protein is you have this long line, then it folds, and you get this 3D structure. And the 3D structure is telling you everything about the functionality of a protein. Protein can do all kinds of things, by the way, in the body. So some of them will do signaling. Okay? They're called hormones. Some of them will be transport. They're called nanomotors. Some of them will be like the gate in your cells. They allow things to go in and out. And some of them will help chemical reaction to happen. They're called enzymes. And so this guy, amylase, is an enzyme. And in the same way that I told you that it all has to do with the 3D structure, you can imagine that it's kind of tricky to get exactly the right structure. So enzymes only work in very specific set of conditions. If you lower the temperature, they don't work quite well. If you increase the temperature, they tend to break down. If you
pH as well.
change the pH, which is like acidic or basic, then they will change the way they fold, and they were not going to work as well. So they can break down, they can just like clump. But if you clump, you're already lost because you change your shape and you're not going to function. So one example to show you that temperature is crucial for proteins is the Siamese cat. Okay? So do you know why a Siamese cat looks like that? What do you say? Physics. Genetics. So it could be genetics. I mean, I'm not asking about the cat part, why it's a Siamese cat and not a different animal. But you see, like, I mean, the Siamese cat are known to have like this white fur and then black fur. And the reason for that is actually not, I mean, it's some genetics, but not only. It's like a mix of genetics and physics, is that Siamese cat, for whatever reason, have a defective enzyme. So their tyrosinase is the enzyme which is responsible for the production of melanin. Okay? So that's what makes your hair dark. And somehow the Siamese cat, with time, started to have a bad version of it. So the version of the tyrosinase that the Siamese cat have is less active if the temperature is high. Okay? So now if you think about a Siamese cat, when you're in the winter, I mean, maybe it's not critical here, but ask your friend on the East Coast, what part of your body are the most exposed to cold? So your nose, your ears, and your hands, okay? So if you look at the body map of a Siamese cat, you realize that their core is fairly warm, but their head, their ears, and their tails and their paws are actually pretty cold. And so when you look at a Siamese cat and you see the color, what you see is actually a color map of the Siamese cat. So that the body, the temperature of the body.
Adorable.
So that was the part about enzymes need the right temperature to work, because here you see it like when it's too cold, it's not working, and you have to have the right temperature. There's like this opposite limit, which is if now you increase and crank up the temperature, what's going to happen is like your very nice structure is just going to collapse. And so when it collapses, it's usually just make a clamp. And an example of that is an egg. Like the yolk is going to cook at 108 Fahrenheit, exactly. Not less, not more. You can go higher and overcook it, but if you go lower, you won't be able to get the protein from the yolk into like this solid part. Okay? So proteins need to be used at the right temperature if you want them to be functional, which means that when you want to use an enzyme in beer, you have to be not too hot, not too cold. If you are too hot, you break it up. If you're too cold, you don't break it, but it's not working yet. Okay? And those are the principles that brewers use to make beer.
We spend a lot of time thinking about that sort of thing.
So once you have, once you have like your barley which consume the walls, the next step is to do the malted barley.
So this is a process, once the seed is germinated and we've converted we've unlocked the carbohydrate matrix and those enzymes are going, then the maltster, will take that grain and put it into a kiln and heat it up to sort of stop that enzyme activity. There's a bunch of different ways that they can do that. And that's where all the color in beer, from the darkest stout to the lightest pilsner, comes from the barley and just the way it's kilned. It's a hot chamber where they dry out the malt and they raise it up to either 120 Fahrenheit or up to as high as 300 Fahrenheit. I think, but that depends. So that just gets you a different degree, different colors. And some stuff like the really, really highly kilned malt, there's the black patent, which you use just a little tiny bit of it, and you get a very dark stout.
Yeah. And so about that, like one thing which I want to stress here is like the kilning is at like typically like fairly low temperature because you got your enzymes. That was the first part of the job. You don't want to kill it yet, Okay, so you make sure that you don't break it down. So you do this step at fairly low temperature. And as Dean was telling you a second ago, in that step you can also do the killing at slightly high temperature to get caramelization. So in chemistry you call it the Maillard reaction, and that's what is going to give you the roasted, brown, sweet chocolate flavor. You have basically the same step happens for coffee as well.
If you've ever been to a brewery on brew day and you smell this great malty character in the air, it's lovely. And then you can just go and eat the grain. It's tasty.
And another story about the kilning, the caramelization, one part is flavors, the other part is what color do you want your beer to be? And so sometimes you can just add up some very dark roast to some extent, just for the color, even though they won't change the flavor very much. And there was this fun story about coloring, which is a few years ago, I think it was in the 80s. Miller wanted to do a completely clear beer.
Bad idea.
And it's extremely hard because, in part, because of this step. And if you Maillard reaction, will always make things turn browner. And so they, with a lot of chemical engineering, they managed to do it. They could get a perfectly clear beer. And nobody bought it because people wanted their beer to be brown or golden or look like a beer. So
something about looking at a beer and just enjoying its colors, I find pleasurable.
So after the previous step, you just take your barley and you just chop it off. Okay, and the rationale for that is you have your enzyme, you have your starch. It's going to be the sugar you want to access, and if you chop it off proper, the water that you're going to put is going to be able to reach it. If it's too big, then it's very hard for water to just get into a material when it's dense and porous. So if it's small enough, then you can access more easily. So that's what you do in that step.
Yeah, the milling is critical for the next step in brewing. Anybody familiar with the brewing process here? Cool. All right, I can tell you anything and you'll believe me. So the milling is very critical for the next step in brewing, which is called mashing, where you steep that milled grain in water. And the water activates the enzymes, which start converting all of that starch that's inside that grain, that grain would normally use to make another plant, which we don't want. So breaking up the grain, breaking up the seed makes the water, gets it more accessible. Gets those enzymes flowing around and moving around and converting all that starch into sugar.
Yeah. So, at that point in the milling, also step before, actually, they don't have to be done in the brewery. You can buy your barley like that. And so now the next step is to take this milled barley to the brewery. So that's a picture of a typical brewery. You may have seen it if you are over 21. So it's basically a bunch of stainless tanks.
It's really pretty.
And the mashing step is what Dean was just describing you. So you have all those tiny, the brown here is representing the milled barley, and the white is the starch. The convention is arbitrary. And so now you put the water, all water around, and it's small enough that you can see, you can easily access. And there's three steps. The gelatinization is your starch is made of rings of sugar, okay? And those rings of sugar, in order to access them, you need to separate them. And so they have something which people call hydrogen bonds. So they're typically some kind of special chemical bonds, which are not real bonds, but just have to do with the orientation of water, okay? But basically what you want to know is that they have bonds which are not so strong and would rather be replaced by water. So you put water, which is now above 60 degrees, 65. So the water is hot and it can have sneak inside the starch and separates the rings of sugars, okay? And that's what makes the gelatinization. Then there's the liquefaction part where those starch start to be chopped off and chewed up by the enzymes. And the saccharification is even reducing the length of the sugar even more, because we'll see that a bit later. The yeast, the small organism who's going to turn the sugar into alcohol, they're, most things in biology, they're lazy, which means that they digest the easy sugar first, and they let the complicated one to chop off at the end. And so the better job you do at providing like a simple sugar to digest, the more alcohol content you will get.
And this is where those amylase enzymes come into play, where they take the long chains of sugar and chop them up into maltose or little smaller pieces of sugar. And this is where a brewer can play with the body and the mouthfeel and the taste and how much of that sugar gets converted into alcohol. By changing the temperature of the mash, you get to sort of tweak what your finished beer is going to come out. This is one of the first places where a brewer can decide, can influence the finished product.
And so that was the part at 65 degrees where the amylase thrives, so it can chop off things. And then you do like one less step at 76 degrees, so it's in Celsius, to basically stop the activity of the enzyme. At this point, you denature it. And that goes down to what Dean was just saying, that when you prepare a beer, like you can change like this temperature a little, you can change the time at which the amylase is functional to change the profile of your beer, but you also want to have some control, which means that when you stop the reaction, you want the reaction to be stopped. And so you want to be able to quench and freeze your product, because otherwise, like if you do that and then for whatever reason, like your production is stopped for an hour, your beer is completely different from one time to another one. So this step at 76 degrees is just allowing you to deactivate all the active enzymes into your beer, and therefore to be able to stock it or move it without having to rush and without any issue of reproducibility.
Yeah, and so this is what your barley looks like after it comes out of the mash. It's those kernels of barley or wheat or whatever, they are they're 97% of the weight of that grain will come out in sugar. So if you taste this after it's been mashed, it's just bland. It's kind of like eating, I don't know, just grain, barley. But this is another test that a brewer can do to make sure that their beer is coming out the way they like. If you taste it and it's still sweet, then maybe you've done something wrong. But this byproduct is good for animal feed. So at the brewery, we would pull out 1,000 kilos of wet grain, and we would put it in tubs, and a farmer would come by the next day and pick it up and feed it to his hogs or his cattle. And there's a company in town here that is using black soldier fly to turn this sort of thing into people food. So it's kind of cool. But we're done with it. We've taken all the sugar out, and now we're going to make some beer.
And so, as Dean was saying, we took all the sugar, which means that at the previous step, at the end, you had like water with sugar. So it's called sweet wort. I forgot to mention it. And then, as the brewer, there's two ways you can guess how much sugar is in your product. There was the first way, which is you chew up your grain and you see if they're still sweet. And that tells you if you did something really wrong, but that doesn't necessarily tell you how much sugar is inside your solution. So the question then is, how can you measure the content of sugar in a solution? Do you have any idea? Yeah? Specific gravity, yes. So the way to do it, if you want to measure the amount of salt or sugar you are in a solution, you can use specific gravity, just like it's an example of specific gravity. If you take the Dead Sea, which has an anomalously high content in salt, it's known that you're going to float a lot better. It has to do with Archimedes' weight, okay? And so now what the brewer is going to do is they take their sweet wort, which is like sugar water, and their deep like the high gravity.
It's a hydrometer is the name of that.
Hygrometer? Okay.
Hydrometer.
Hydrometer.
Yeah.
And the more sugar there is, the higher the hygrometer will be. Okay, it's going to float more. And it's been calibrated, and then you can directly read on it the specific gravity, which is the ratio between the density of your sugar water and the density of water. Okay, so that gives you a number. And the definition for brewer is one plateau is 1% extract sugar by weight in solution. So that's how brewers know what is the content of sugar in their beer before they start all the fermentation process. Okay, that's for the initial point.
And so, why are we concerned about how much sugar is in our beer, or our wort? Well, the yeast is going to take that sugar and turn it into, among other two important things, carbon dioxide and, there we go, that's what we're here for, right? So the more sugar you put in there, theoretically, the more alcohol you're going to get out of it. And in some places, it's also used for tax purposes, but we're not going to concern ourselves with that because it's not what we do. But a lot of that, and so it's your first real initial sort of empirical thing that you can measure in the brewing process to make sure you're on track.
Okay, and so you have this solution of like sweet water, and as Dean was saying a second ago, you can have for the first time a clue of whether you're doing things right. And so the next step is the wort boiling. So you're going to take your sweet water and you're going to add up the hop and you're going to boil the whole thing. And so the hop, they're like this really cool flower, and they're providing all the bitterness taste of the beer. Okay? And they also happen, I mean, the story of the hop and beer started by serendipity. Like some brewers realized that if they're adding hop to their production, it was not getting spoiled. So they started to put more hop, and hop has actually antibacterial properties.
And
so
it was recently discovered that it also has antiviral properties as well as antibacterial.
So it's both providing taste and very important for the stability of the product. So just like a quick story about hop, like who do you think is the first producer of hop in the world? Germany. Yes. Second?
Czech Republic.
No, France doesn't do beer
Britain.
very much.
Well, probably
USA? USA?
America.
And third?
UK.
Ethiopia.
What?
According to my number, Ethiopia.
Ethiopia.
Yeah,
Okay,
so,
that's new to me.
It's a major thrust of the Ethiopian economy is the growth of hop.
Hops grow in a certain specific latitude band, which is why you get it in Germany and the UK and the Pacific Northwest. And so I guess Ethiopia is at the southern side of that. Oh, yeah, what am I going to say? Okay, all right, so hops, we're talking about hops. They're awesome. They do 5 things for your beer. So we already talked about the preservative properties of them. We already said the bitterness. What else do they do? Anybody got any ideas? Flavor, that's good. 2 more.
Color?
No color. Something that goes along with flavor. Aroma, very good. And they make your beer awesome. Because you get bitterness out of this, which is going to balance out the sweetness of your beer in the end. And so this is another place where the brewery can change their recipes. There are many, many different varieties of hops. And this is all kinds of things that you can do. This is one of the more important ingredients in beer.
Do you want to say a word about the low temperature
About the what?
pellets? What you were telling me earlier about
Yeah, so brewers have traditionally used hops in these 2 forms here. The whole cone is what they called, and the pelletized, rabbit pellets kind of thing. But this is a lot of vegetal matter to put into your beer, and it absorbs your wort, and it's going to be left behind. So to get efficiencies, there's a new process called cryohops, where they do some sort of CO2 extraction to get out the important parts. But as you go down, as it's processed from the cone to the pellet, you lose a little bit of something. You lose a little bit of the compounds that are in there. So a lot of craft brewers will only use whole cone hops, and most everybody uses these pellets because they're super easy to work with, and they keep.
Okay, so you take your hop, and then you put them in the wort for boiling. And one of the essential components of the hop is that they have like this, when you look at the hop, they have like this gland which contain like a yellow sticky powder. Okay?
Lupulin.
Yes. And this lupulin, as one of its main components is humulin. And so when you put the hop under heat, this humulon is going to convert into alpha acids, iso-alpha acids. So humulon is already an alpha acid, and here you have iso-alpha acid. And those are the components which are responsible for the bitterness and for the antibacterial role of the beer.
What's happening in the boil here is you get the humulus, and you get these alpha acids come out of the hops and beta acids, and then during the course of the boil, they get isomerized, so they get turned into these long chains of the same kind of acid, and that's what gives you bitterness in beer. The alpha acids themselves do not give you bitterness, but boiling is what takes it and turns it into that bittering compound. And then you got the beta acids too, which we got a frowny face over here. They're not quite as good as the alpha acids, but something interesting that people discovered not too long ago was if you age a beer, aging beer doesn't necessarily make it better or worse, it just makes it different. But as you age a beer, the alpha acids kind of fall off, and the beta acids become more expressed as they oxidize, and beta acids become more bitter. They sort of mimic the alpha acids as they age. So like if you get a beer that has a good balance of alpha and beta acids, then you get, then it ages well. Alcohol also helps aging too because it acts as a preservative. Cool. But go.
Sorry. So then there's like this one issue with the alpha acids, iso-alpha acids, is that they tend to break down if you shine the light on them or you expose them to light between like in the low UV range, so like 350 nanometers to 550, but it's basically like blue and UV, okay? Like this big molecule is going to break down, and it's going to break down around here, and you're going to get like this 3-methyl-but-2-N1 thiol, MBT. It's going to remind you your chemistry classes. And the problem with those is they have a skunky smell, okay? And obviously, it's not something which is desirable. And the main issue with that, there's a lot of, when you expose things to UV, they tend to degrade. What happened, which is specific to MBT, is we're actually anomalously sensitive to MBT. So we can detect 7 nanogram per liter, so it's like roughly a teaspoon in 100 yards cube. So that's like roughly the threshold of detection for a shark with blood. And so now what's happening is for you to understand and to have a better sense of what is light-struck beer, which is beer which has been turned into skunk beer because of sun, we have our students, a course of very nice students, who are bringing you some fragrance slips for two kinds of beer. So if you're, you should be able to detect it on your own, but if your strip is white, then you should have unstruck beer, so it's proper beer. If your strip is blue, like here, then you are smelling skunk beer. It doesn't smell good. Okay? So this way you can have a better grasp of the difference. One thing about MBT, by the way, is it smells like skunk, but it doesn't come into the composition of the skunk spray by the skunk. And then, because I told you that it all happens if you shine like UV, so it's Corona. So you have to set your smell at the Corona level. So it doesn't smell great, but it can smell worse. And so here you have like, I told you it has to, you have to shine like in the blue or in the UV. So how can you protect your beer from being light struck? There are
colored bottles, yeah.
Cover bottles. So the easy thing is like the can. So there's like more and more brewery are using cans because they provide an actual 100% perfect protection from UV. Another strategy is to use a bottle color who's going to absorb those wavelengths. So brown glass bottles work well. But something you don't want to do is have a clear bottle or a green bottle. So clear bottles are the bottles that Corona decided to go with. And Corona, as you can smell, gets light struck and smells bad. So Heineken, who see themselves as a nicer beer, wanted their beer not to be light struck, but for marketing reason, they didn't want to change the color of the bottle. There was too much history with the green bottle of Heineken to change it. So Heineken actually heavily invested in engineering so that you can actually change one of the double bond here so that it cannot convert into MBT.
Yeah.
So the Heineken bottle doesn't light struck, so you can leave it in the sun. It's not going to start smelling like skunk. And it's because Heineken decided to invest on research rather than changing the color of the bottle.
That's what you can do if you have a lot of money.
So yeah, for that reason, most craft breweries use cans because that's a very valid solution without any of the chemistry complexity. So we go back to the word boiling. So the boil has like 5 function, which is a hop extraction. So you put that in the sweet, your hops in the sweet wort, and then you heat it up, and you're gonna extract like the alpha isoacids into your beer. You're also gonna get some caramelization or the so-called Maillard reaction. That's gonna give you some additional flavor. And another thing which is happening during the boiling step is that it's going to get rid of volatile off compounds. So for example, like at this step, you tend to have like a few sulfuric compounds, which is going to give you give your beer like a cooked vegetable taste.
Dimethyl sulfide.
Yes, dimethyl sulfide. And so you don't want this cooked vegetable taste to your beer. So luckily, it goes away at this step. Boiling is also great because it sterilizes your beer. It gets rid of whatever bacteria were left in the process and the wild yeast.
This is why beer is safer to drink than water.
And finally, it takes care of the cognition of proteins. Like during those steps, there's a lot of proteins inside the beer, and you want to get rid of them. So you heat up, your protein's going to denature, and they're going to start to clump. And then they're just going to fall down. And so if you get rid of what is at the bottom, you get rid of all the proteins, and you get a better beer.
Yeah, some of those proteins carry over from the mash, the grain, and they tend to be bitter in the wrong kind of way and vegetal in the wrong kind of way. So boiling really kind of smashes them together, makes them bigger clumps, and they fall out, which we're going to talk about as we do the work.
So the next step is to get rid of like all those clumps. And so you put your beer in the whirlpool. And your boiling wort is injecting this whirlpool, which is like making the boiling wort turn around, and then you end up with all the trub stacking up at the center.
And that's not just a weird French accent. The word is trub.
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 Trub. Sorry.
The Germans give us some cool words for the brewing process.
And so when actually I saw that in the brewery, I was like, oh, that's really odd. Why is your trub going to the center? Because when I spin stuff, they go at the edge. And I mean, you all know this experience. If you go on this post and you spin the post, then you get like repelled from the center by centrifugal forces. And so what's happening to the tube? And so when I saw that, I was really puzzled. But it's actually something which is known. It's called the tea leaf paradox, which is if you take a cup of tea and you swirl it, then you end up with all your tea leaves in the center, which is very unusual. For something that has centrifugal force. And so actually the paradox was solved a while ago by somebody who did some other cool stuff in physics. And so Einstein was discussing, and he was doing his tea, and he was like, this is just not right. And so he actually wrote down like a small article where he said like, oh, I found out for the tea leaf paradox. I said, I begin with a little experiment which anybody can easily repeat. So we're going to do the experiment. So you take a cup, okay, and you swirl it, and you have your liquid. So here you have the centrifugal force, okay? But because your container is finite, your fluid has to come back. The liquid is incompressible, which means that it's hitting the wall and then it's coming down, okay? So you will make 2 swirls like that. And if you're heavy, then you follow those lines, and then you end up there. And so the tea leaf paradox is just an effect of the size of your container. And that's why the trub ends up in the center and not at the edge.
And that's why we as brewers pay engineers to design our tanks.
So that's the code. And so
Fermentation. Okay, so this is where the magic happens. As a brewer, I like to say that we just sort of make the perfect environment for yeast to do its thing, because this is where a lot of biochemical processes happen, and just the magic of taking wort, which if you taste raw wort, it's a little weird. It's very sweet. It's very bitter. And then you put it into a tank for 3 weeks, and beer comes out. There's a little bit more to do between that, but this is where really everything goes wrong or right.
So just to be a bit more quantitative on the wort, at this point, it's like a bunch of sugar plus like a lot of isoalpha acid, so that's the bitterness and the sweetness that Dean was mentioning. And so you have like glucose, which is 15%, fructose, sucrose, maltose, maltotriose, and so those are more and more complex sugar. So the easiest one the shortest one and the easiest one to digest is glucose. So who's going to digest them and who's going to turn them into alcohol? So the person who's doing that, or like the organism who's doing that, is the yeast. So the yeast is a very simple organism that's a fungus, like mushrooms, okay? So there is like roughly 500 different types of yeast, and they've been sequenced. They were the first organism to be fully sequenced, and they have 6,000 genes. So you can see here that they have like those circles here. They're like buds. So every time they divide, they get a scar. And that's what you can see here. So you can count their age by counting how many scars they have.
Yeah, and so this little guy, or excuse me, gal, because that's a little daughter cell coming off of it, has gone through, we can count, it's probably its 4th division. And that's about as many, we're going to get into respiration and the other stuff, but that's about as many divisions as a yeast cell will go through when it gets into wort for the first time.
So wild yeast are diploid, so that's like a complicated word to tell you that they have 2 copies of each chromosome, okay? And they form spores to mate, okay? So they have a mating process. But when you think about like brewing yeast are very peculiar. They're not like wild yeast at all, because the way a brewer brews a beer, he makes an attempt, he tastes the beer, if he likes it, he keeps it, if he doesn't like it, he throws it away. So when you do that, you obviously change and skew the type of yeast you want by a lot. And as a consequence, like to some extent, you can say that brewing beer is like accelerated Darwinism for yeast, okay? So that you really end up selecting a very specific profile of organism. And out of that came out the brewing yeast. And so it's not a wild yeast at all, it's like a pet yeast. So they're polyploid, so it means that they have many copies of their chromosomes, and they don't mate, and they only divide. So what this polyploidy and this no mating gives you, it gives you an insane stability of your yeast, because like whatever mutation you do, it's not going to change anything, because they have many chromosomes, so they still have a copy, and they don't mate, so they don't mix up their flavor. Actually, that's certainly one of the reasons brewers like them. That was not meant to be that, but that's the outcome.
Yeah, we like our things consistent.
And so these 2 types of brewing yeast is like Cerevisiae, which is a top fermenting yeast at warm temperature, which is used for ale. There's like Carlsbergensis, which is a bottom fermenting yeast at low temperature, which is used for lager. And there's basically all the other ones, which are used for Lambic beer and Belgian beers, because one of the main traits of those, they're made into a wooden system, wooden barrels, which are not necessarily very well controlled. And part of the taste will come from the barrel, which means that some yeast live there, and they're giving you the specificity of your beer, but who is living there is not always clear. So that's why, for example, like brewers or even people who do wine would exchange barrels and wood to carry a profile of beer.
Ever had a Jester King beer? They're pretty famous in this part of Texas for making wild beers and stuff. So they'll have big wooden vats where they sort of encourage these wild yeasts and microbes to grow, because it adds a lot of complexity. But it's dangerous because you can spoil your beer. Not dangerous to health-wise, but just dangerous because you're going to put some product into a barrel and wait for 6 months, and maybe you get bad, maybe it doesn't, maybe it fails. So mostly brewers are concerned with keeping out the bacteria, the wild yeast, and coddling and making the perfect place for the Cerevisiae. Yeah, you have a question?
Oh,
So,
good.
there are basically two broad categories of beer, and it comes down to which one of these species of yeast you select. So a top fermenting, the ale yeast, that makes all of your ales, and as the beer ferments, as the yeast is there in the sugar, it forms this dense, rocky, brown head on top of the beer, and it's bubbling and roiling away, and it looks really cool. Whereas lagers, the other category, the Saccharomyces carlsbergiensis. Oh, and by the way, Cerevisiae, Saccharomyces cerevisiae, that's the same yeast used to make bread. So they're very, very similar. Carlsbergiensis is a bottom fermenting yeast. That's all lagers are made that way, and that yeast just sort of stays on the bottom and does this thing. It's not quite as interesting to look at, but lagers are my preferred beers, so it's all good.
And I can tell you like a funny story about like selection pressure, because I told you that like brewing yeast is basically like pet yeast. So there was like this brewer in San Diego called White Labs. They did like a collaboration with Illumina. So Illumina, I don't know if you know them. They're a $1 billion company. Their job is to sequence people and things. So that's what they do. And they said, okay, let's sequence all the strains we have. So all the kind of yeast we have. So they did a catalog of all the yeast, and they know exactly where are which genes, and they did all that. And so
a strain of yeast is sort of like I said, there are two different broad categories. There's like dogs and cats, and then there are lots of different breeds, which gives you your different strains of yeast.
So like strains are like sub types within a category. Okay, so there's 500 yeast strains within those three categories. Okay, so you can do a lot of different beers, even using just like an ale or lager. And so they had all these different strains, which are like subspecies, and they sequence all of them. Okay? And one of the reasons why they do that is actually White Labs is a bit more than a brewer. It's also a conservation space for yeast. Because yeast are living organisms, so they're non-GMOs, their own natural organism. So because they're natural and non-GMOs, then they cannot be patented. Okay? So each brewer is using a strain or a mix of strain, but if for whatever reason their brewery gets flooded, if they don't have a copy of this strain, they lose all the profile of their beer. And so they ask White Labs, Chris White, who has like actually a background in science, who has a PhD in chemistry, to store their yeast so that if anything happened, they can still get it back. So they sequence everything, and then they have like 96 strains. And they say, okay, what can we do with that? We do the sequencing, it was cool. We wrote a paper. Can we do anything fun with that? So they say, okay, let's do a beer. So they take the 96 strains and they put them into the sweet wort. You would never do that. I mean, it would be like a hell of a complicated beer. You'd have no idea what is going to come out. But they say, I mean, we have the strain, we should try. And they repeated the process. So they put the yeast, they put the wort, they make a beer, they take like the leftover yeast, and they repeat a few times. And what do you think they got after like 3 or 4 batches? What kind of beer do you think they get?
Which?
Yeah, wild. Okay? So that's exactly what this picture is telling you. So they had like 91 out of the 96, they had 91 brewing yeast, and 5 of them were like wild yeast. And at the end, what they got was a beer which was exactly what they would have gotten if they just started with 5 wild yeast at the beginning. They completely eradicated all the brewing yeast flavor in their production. So now we're going to go to the, biochemistry. I'm not going to get too much into the detail, but like the job of the yeast is to get your sugar into alcohol, okay? And so there's 2 ways yeast can have a metabolism. Metabolism is how you get sugar to get like energy. So ATP, that's the token of energy for organism. That's how you pay. So you see there's 2 ways you can have metabolism for yeast. There's the aerobic respiration. So it's just saying that they're allowed to breathe oxygen. So the yeast can take sugar, that's this guy, and oxygen and get 28 ATP. That's a lot of ATP.
It's a lot of ATP.
Or there's this other way, which is the anaerobic respiration, where they take like sugar, but because it's anaerobic, they're not allowed to get oxygen anymore. And now they get only 2 ATPs. And so you could ask yourself, like clearly 2 is less than 28. And so you could ask yourself, why would the yeast ever use anaerobic respiration? It's so inefficient.
That's where all the great flavors come from.
And the reason, from an evolution point of view, is that when they do that, of course they give away 26 ATP. So they give away a lot of energy. But they make ethanol. And yeast can live in ethanol, but most organisms can't. So the yeast indeed gets less energy, but it gets protected from all environmental attacks. And so from an evolution point of view, that's why a lot of yeast have evolved to use the anaerobic respiration very well.
It's swimming around in that sweet wort, farting carbon dioxide and peeing alcohol and just making it safe for itself and yeah.
So a couple more details about the anaerobic metabolism. So it's just like to tell you a bit more, but I mean, I don't want to stress too many of the details. But basically, you have the sugar, and then you end up with something which is a pyruvate. Okay, and this pyruvate for the yeast is going to be broken down by something which is Pyruvate Decarboxylase, which is an enzyme. So the yeast has an enzyme which is going to break down this guy into acetaldehyde, and another enzyme, which is the alcohol dehydrogenase, is going to break down the acetaldehyde into alcohol. Okay, so at the end, you started with sugar, and you ended up with alcohol. And that's what makes the alcohol from the sugar in the yeast.
And as your beer is fermenting, you can acetaldehyde is a very green apple flavor smell, and so as your beer is fermenting, you can actually taste green apple in your beer, but the yeast will clean that up as it goes along and finishes out its process.
So about the anaerobic process, I mean, yeast can function aerobically. We can also function aerobically. So we are not designed for that. That's typically what happens when you go beyond your limit when you practice sport. And so that's when you get sore. And so the main difference between us and the yeast is that the step 2 for the yeast has a pyruvate decarboxylase, which allows to make the acetaldehyde and then the alcohol. And we are not having this enzyme. And so instead of that, we have the lactic dehydrogenase. Okay? So we take the pyruvate and then we make lactate. And so the drama of that is when we work out, instead of being drunk, we get sore. Because the lactate is what makes us sore.
Not as good.
And so in the fermentation step, like at this point, if you want to know if everything is working well, you can take part of your sweet wort or whatever is in the tank and like pitch yeast. So you look at how many yeast are alive. Okay? Because you want to make sure that something they didn't get damaged by some bacteria or something happened. You started from a batch of yeast who was not very viable and a lot of them died. That would clearly impact how much alcohol you could produce because they're going to convert it in sugar. So you do like this count.
If you don't pitch enough yeast, your beer doesn't ferment, and it takes forever in the tank, and then you're going to make more beer, and somebody's asking for your beer, and yeah, you just don't want to keep your beer in the tank for very long. So pitch enough yeast.
And so the fermentation is like has 4 steps. The first step is the lag phase. That's basically a step where there's still some oxygen in the tank, and the cells, the yeast, will use it to build walls, cell walls, lipid walls. As Dean was telling you, you could see the buds, the scar buds, that's how many times they divide. Okay? And so you start with a few yeast, and you want a lot more yeast in your tank in order to ferment. Okay? So they're going to divide, but every time you make a new yeast, you need like to be able to build lipidic wall, and that takes oxygen. So that's what happens in this phase, which is like typically 0 to 15 hours. Then you have like the exponential growth, where you have like the division of all the yeast and the consumption of the sugar. And at this point, so the sugars are consumed by complexity, first glucose, then fructose, then sucrose, and maltose. And at this point, you have the green beer, and as Dean was saying, with acetaldehyde. And then you let the different yeast sediment, and you will be able to get your beer. So here you can see it's a picture of a tank, and with different dates, and each date is like the plateau level of your beer, which is basically the sugar content. Okay? So the more you wait, you see the lower the number is. So you take your beer and you see that the specific gravity is going down. So there's less sugar. If there's less sugar, there's more beer. And that allows you to know how much alcoholic degree has your beer. Yes?
If you add just a ton of yeast at the very beginning of fermentation, can you speed up the total fermentation process?
Yeah, but there's a potential to produce off flavors as well. If they just start, if they're in an oxygen environment, the metabolic pathways are going to be a little bit different. And it's not, I mean, it's also a lot of yeast to store and hang up. So you're adding a big volume of liquid to your bigger volume of wort, so you're going to get less beer in the end. So it's a fine balance that we gotta walk. Another cool thing about that this process is there's another we talked about acetaldehyde, but there's another compound that yeast produce in their metabolism called diacetyl, which is a butter popcorn flavor. So I am completely blind. I'm pretty badly blind to diacetyl. I can drink some beer that other people recognize as full of diacetyl, and I don't taste it. And so when we did our sensory analysis to release a beer, I would have my guy Parker, who was very sensitive to diacetyl, let me know if there was any diacetyl in there, because you don't really want to release butter popcorn beer unless it's on the label.
And so at this point, you did all this work to get like a glass of beer.
Yeah.
Okay? So
the yeast is doing most of the work.
yeah, the yeast did the work. And so you have your beer, but like it can be a bit hazy. And since the beginning of the 20th century, it became like marketingly better to have a clear beer. People started to believe or to think that a clear beer is a better beer. And so now you need to clarify your beer. So with the rise of microbrewery, this has changed a little. For example, now people want their IPA to have some haziness, and they associate the haziness to the freshness of the beer. It means that it's less processed. On the other hand, if you serve them, I mean, Chris from Blackwater and Dean was confirming that if you bring a lager which has not been clarified, then you're guaranteed to get it sent back. Okay? So it's like a lot of the clarification process is not so much about the taste of the beer. It may change the flavor a little.
A little bit, not much.
But it has a lot to do with how people perceive and what they consider a good beer or a beer which has not been processed enough. So how do you do the clarification? So you have like all those proteins which are like typically the reason why it's not clear is you have like some yeast in solution in your beer, and you have like some proteins and you want to get rid of them. So one way to do it is to coagulate them and let the whole thing fall down. So one way you can do it is you can use isinglass. So that's a collagen protein from the bladder of an exotic fish. And he has some positive regions and he has some negative regions. And because he has both, it guarantees that whatever is in solution is going to either stick to the plus or stick to the minus. And then they make a clump, and the clump is heavy enough and they fall down. And that was like, I think, what people use for long time for clarification. One issue with that, can you see an issue of that? Nature conservation. No. What do you say?
Yes.
It's not hard to get. No, you can get those fish. You can get their bladder. People don't eat it. It's not vegan.
Yeah.
So because of the vegan market, people had to come up.
We don't know too many vegans here in Texas.
What do you say?
We don't know very many vegans here in Texas.
So for California market,
Yeah.
they had to change. And so they started to use like silica particles. So it's just like tiny glass beads, which are plus or minus. You throw them, and then they catch whatever, and they fall down. So you decide which one sounds the best to drink, but at least it allowed the beer to be vegan.
Would you like fish bladders or silica in your beer?
And so at this step, we can go to the bar, and an important component of beer that we never touched on so far is foam. And foam is like really important on like the experience, what the beer looks like, what the beer tastes like, and you want your foam to be nice and to stay nice. So first question is, what if foam? So this guy is actually very famous in San Diego. He's making bubbles on the beach all day. And so if you want to have a good
bad
foam,
life.
a good foam, a foam is an assembly of bubbles, okay? And bubbles are just like thin film of water with air inside and outside. And so how can you stabilize a thin film of water? So you use soap. You know that when you are a kid, you blow bubbles and you use soapy water. And the reason for that is because soap is a surfactant. So surfactant is this kind of like molecule which has an hydrophilic head and an hydrophobic tail. What does it say? What does it mean? It means that the head likes water and the tail doesn't. Okay? So now, if you put like a water and soap, what do you get? Do you think that your tail is going to go into the water film? No, your tail doesn't like water. So it's not going to do that. What's going to happen is you're going to form a film where all the head of your soap is going to get into the water, all the tails are going to be outside, and therefore you get something which is now happy and stable. So that's how you get like the soap and how the bubbles can be stable. And so in your beer, like there is no soap, but what is going to play the role of a surfactant, like this thing which is going to coat your bubble very well, is the protein. And the reason for that is because proteins are this complicated mess, so you always guarantee that you must have at least one part which likes water and one part which doesn't, so it's going to deform so that it can do that. And so now you have your beer, you have the foam on top, and so like it's air here and like liquid with like the surfactant, and there's two ways your foam can go bad. One way is coalescence, which means that like two of your bubble will just merge, and so it means that like the surfactant coating was not that good. And the other way is the little bubbles dissolve into the big ones. So this one you can't do anything against it. That's physics. It's called Oswald ripening, and it's going to happen anyway, but it's very slow. So usually what you want to avoid is the coalescence. So I will show you an example of coalescence. Let's take one beer.
Please. The camera.
Up. And so if I take, like, let's say a chip is like, what do you think, hydrophilic or hydrophobic? It's oily. Oil likes water or doesn't like it? Does like, so oil is hydrophobic, okay? So what's going to happen? So what's going to happen is if I take my beer and have the foam and I put like something which is greasy or oily. Okay. If I put something which is greasy or oily, my oil, my fat, is going to go on my shield of nice surfactant and it's going to make puncture. Okay? And all my foam will break down. So I can show you.
Goodbye, foam.
And you can see the foam has a hole in the middle. Can you see it?
There's a little bit too much light on that. I can tell you it is going down.
You will see in just like a second the whole foam will be gone. And so that's actually something which is very... It's Corona.
We have
And
invented
that's
potato
something
beer.
which is of huge concern for brewers in breweries is you don't want your glass to be oily, because if you, for example, like your waiter is putting their finger into the glass, and I'm not talking about hygiene issues, you just gonna have like some sebum, which is like oil from the skin, and then the customer will get their beer, and then the foam will spontaneously destabilize. And the same way, most brewers don't provide peanuts at the table, or like craft breweries, as opposed to divey bars, because dive bars do what they want. But craft breweries believe that it's going to make the foam a lot worse. So you can see after like, you've all had a Corona before. It usually doesn't get better with time, but it takes over a minute to get absolutely no foam on top. One last thing, oops. So that's what I wanted to show you here. You just put the fat and you get the puncture. Another thing I wanted to mention about foam is that bubbles are like a bit special, which is that bubbles can grow, but they only exist if they're big enough. So if you take a beer and you pour it into a glass where there is no nucleation site, so nucleation site is at some point, you have to, your bubble can only start growing if it has like a point to start, okay? And so if there is none of those nucleation points, you don't get any foam. So I'm gonna do the experiment. I don't guarantee it's gonna work because I cleaned this bottle in San Diego a couple days ago, so it's super clean. So it's like lab clean, okay? So that the thing is at zero dust. In principle, there's zero dust. Let's see if it remains like that. And I'm gonna pour more Corona, and we'll see what happens.
It's the science in the field, y'all.
Camera.
And one of the hardest things that I have at my restaurant is getting my the staff to make sure that the glasses are clean when they come back from the kitchen, because this looks pretty good. I don't see any indication of dirty glass, so that's great.
So yeah, this glass was supposed to be very clean, so it didn't go quite the way I was hoping to show you. But if you can do it with like clean and fresh glass, so you have absolutely zero dust, and you pour your beer, and it's going to stay completely flat. And that's very, very surprising.
You might need to work on your pouring technique.
What's that?
Pouring technique.
Yeah. Another thing, you can also use that. For example, here, those are more clean glasses, which are etched at the bottom with like laser etch to provide nucleation sites. And we should be able to see that most of the bubbles really come from.
Yeah. So you see here, there's no bubbles on the side of the glass. That's an indication of a very clean glass. If you get your beer from your restaurant and there's bubbles all along the outside, that's a dirty glass. And do with it what you will. But this is a nice, clean glass. Don't waste beer, y'all.
Another thing about foam, so I will need, you're coming? Yeah. And second volunteer, you're coming? Come.
Give them a round of applause, guys.
Yes. So I'm going to give you...
Who's getting nervous right now?
And can I have, where is the water? Here.
You can use that, that's fine, yeah.
And I'm looking for, okay. So can you, yes. No, actually no camera, I mean, they're gonna run. Can you try to run, can you do a race, both of you? Come here, Nid. And TG. So can you run like here and forward and back? And let's see who comes first. 1, 2, 3.
Good.
Okay, back. Nice.
All right.
Okay, thank you. So what do you think of what just happened? What is that? So have you ever tried to do that with, like, if I give you the same glass full of water or coffee? Up to that point, you agree they were both full, and I ask you to run and back, how much coffee would be there on the ground? So what happened?
The moral of the story is coffee is not as important as beer.
So you all know that when you walk with your coffee, actually, if you don't put the lid, it's so hard not to get coffee everywhere. On the other end, they just should, and I asked both of them because presumably they don't have too much experience running with beer. So it's not like they could make up for compensation like drunk people would. So you could see that when you run with a beer, it never slushes. Do you have any idea why? No, because it is water. I mean, it's really like water. Foam.
That's the
So the
foam.
top, the difference is foam. Okay? So the foam is going to play the role of a damper. And so whatever motion of the water, there's actually, if you look at the motion below, it's roughly the same. But the difference is in water, like if for coffee, it's going to slosh, but for beer, the motion at the lower interface is not going to propagate on top because it's going to be completely dampened by this damper of foam. And so that's something that physicists like realized really recently. There was like a few papers like 3-4 years ago, and it's actually like in the manual from the 70s about how to be a good waiter. I found out there was like never forget the foam on your beer because otherwise you will put beer all over the room. So make sure that you have a good head, and then you can just walk across and nothing bad will happen. And so to finish this presentation, I'm going to tell you about the science of something you may have done. Younger, I need a ring. Can you... he's also going to do on camera. Apparently, he can open beer with his ring, so I think everybody should see that. Can you do it now on the camera?
$1,000 right here.
Yeah.
Nice. Okay. Thank you. So beer tapping. Dean, please.
I've never done this, so let's see. There we go. This is how you be a jerk to your friends.
Could everyone see, or should we do it again on camera?
All right.
Do it again on camera. Okay. So more Corona. Please. You can even.
I'm trying to do it on camera.
Are you a good beer tapper? You want to do it? Okay. This one is not. So this one was also light strike beer. So maybe when it spends too much time in the sun, it doesn't do it
Maybe.
as well. But you could see you get like this huge, and you've all done that before. Yeah.
That was my first time.
And so what's happening
alcohol
when you
abuse.
beer tap? So I will show you like the scientific version of that. So it's actually something. It's based on a story in a paper called PRL. So that's kind of like one of the coolest paper you can publish if you're a physicist. So it's I'm going to show you what we just did, but with a super high-speed camera, so it's 1,000 times slower than in real time. And so the shock happens, and then you see like all those bubbles coming up. And obviously it's very slow. I mean, in real time it's only 1 second. And you see those bubbles everywhere, and then you will see like a mess around the bottle. Yeah.
No.
So that's a good. So what is happening is when you tap the bottle from the top, you actually make a shock wave. So that's what those little red things are, okay? And so if you look at the bubble, so this is just like a bubble inside the bottle, like normal bubble in the beer. So it's like the size is roughly like a fraction of a millimeter, like 1 millimeter or a bit less. And so let's see what happened to this bubble when the shock wave comes, like moving, shaking, and then it explodes. So you have to see, like, this whole movie was 1 millisecond. So it's really like 10,000 times slower. And so you went from one bubble to 1 million bubbles. And those new bubbles, they're very tiny. They're like 1 micron. So they're 1,000 times smaller. And so now you have this thing which is, this beer, of course, has like CO2 which was dissolved. That's why you had bubble in the first place. And so it's very hard to fill up by something called diffusion. If you're big, like the CO2 won't get in very well inside, or it's going to be very slow. But if you're smaller, you can grow very quickly. So you had one bubble, which size was mainly set around 1 millimeter. And you made a shock wave, and you made it 1 million bubbles. And then those million bubbles, they will immediately capture CO2 inside the solution and become 1 million bubbles of 1 millimeter. and that's what makes the slushing and the gushing from the beer. And with that, that was the last thing I wanted, and we wanted to tell you tonight for this presentation, and I thank you all for your attention.
Any questions out there? Yeah.
So what's the difference between a wheat beer and
So the question is, what's the difference?
Repeat the question.
The question is, what's the difference between a wheat beer and other beers? Beer is made primarily with barley, but it also can include wheat and rye. And so a wheat beer simply is made with a larger portion of wheat, 50% or more. And it gives slightly different characteristics in the malt profile. Heck, just hit me. I'll repeat it. Or not.
you are now?
Yes.
Don't do that. Let me be dumb. It's fine. What's your favorite kind of beer?
The one right in front of me right now.
Who wants this now? Anyone?
Question in the back, yeah. I need a moderator. There we go.
There we go.
All right, so why do you need water? Why can't you just dump sugar in the water? Like sugar, like pounds?
So why can't you dump sugar? I don't think that mic's on. Why can't you dump sugar in the?
I can speak loud.
Yeah. Because sugar is a very simple. That's just glucose, and you get kind of this boring flavor out of it. Whereas the sugars that come out of the grain are much more complex, and so a lot of those carry on through into the finished beer because the yeast doesn't digest it, so you get more complex flavor. And certain beers like Belgian triples do augment with sugar, pure cane sugar, but that just simply turns into alcohol.
Yes, I mean, if I wanted to be provocative, I think it really depends on whether you want to do vodka or something which can be enjoyed. Obviously, if you just want to get ethanol, simplicity is key. If you want something which is palatable, then you may want a bit more complexity.
A light body and highly alcoholic. Pass the mic around.
I actually have two questions. My father was a tavern owner, and I always observed him when he put the beer in a glass from the tap, he always made sure that the glass was on an angle. Why is that? That's my first question. My second question is, does the temperature of the container matter as far as the head?
These are very related questions, in fact. What's cool about carbon dioxide is it actually wants to stay in solution. It wants to stay dissolved in there. And unless something causes it like a temperature change or a physical shock, it won't come out. And so if you pour a beer straight up, you get a lot of foam. If you pour a beer down the slide, you're being a lot more gentle to it, so you don't get a massive amount of foam. And the same with temperature. The colder a liquid is, the more carbon dioxide you can cram into that. And I do not condone using frozen mugs because that also changes your experience. But the colder a glass is, the more likely that carbon dioxide is going to stay in it. It also keeps your beer colder, which means you don't perceive as many flavors. Flavors are activated by warmth. So that's why people serve you garbage beer in cold glasses, so you don't taste it.
I mean, about the carbon dioxide, there's an experience that most of you may have done before, which is if you drink Coke, like not beer but Coke, you all know that if you take a bottle of Coke and warm it up or forget it into your car, it's going to be very flat afterwards. And that's just what Dean was telling you, that CO2 doesn't stay very well in suspension in the liquid. When you increase the temperature, it's just going to go away. And so...
There was a question over here somewhere.
Yeah, it was back to the sugar. During the Super Bowl, there was the ad where they were talking about fructose corn syrup. And so you said, more sugar would equal more alcohol, which you know isn't the case with the Bud Light or Coors Light.
That's if you all saw the Super Bowl commercial, I forgot who was saying that they don't use high fructose corn syrup. That's kind of more like a marketing ploy that they're trying to differentiate themselves on. High fructose corn syrup will convert into alcohol, just like sugar does. So yeah, it's.
Are they cheating are they adding in the fermentation process and cheating the front end and they're not creating their own?
What they're doing is they're saving money on they're not using as much grain, which is going to be more expensive than high fructose corn syrup. So they're trying to save money that way and trying to convince you that it's better for you.
Yeah, corn syrup is on top of that. Corn syrup is complicated because there's also a lot of tax relief coming with using corn syrup in the US. So you can get cheaper by adding corn syrup. So
But it doesn't add any flavor.
no, same thing for muffins. Or there's actually a lot of things you can buy which have corn syrup. Best case scenario, don't taste it, but usually it's going to make it a lot richer and not necessarily very healthy. But
What is the typical concentration of sugar in the wort? In other words, how many Platos?
Sure. Most of my beers start out around 12 Plato, which is 12% sugar by weight in water. That will get you about a 5% beer, or 4.5% beer alcohol by volume. Brewers will go up to maybe 20 Plato, which is 20% by weight. And you will get a highly alcoholic 12%, 15% beer if your yeast can survive in its own waste long enough to convert all that sugar into alcohol.
With a higher incidence of gluten intolerance in our society today, what are the other grains that are being used for beer so people who have gluten intolerance can still enjoy the world's best drink?
Sure. There's some research into sorghum, but more research is going into adding enzymes into the beer that will actually break down all that gluten. So you get what's called gluten-removed beer, or drink cider. But instead of using a different kind of grain, they just take the gluten out by chemical process or enzymatic process, biological processes.
Luis, can you shout from there?
What about light beer?
What about light beer?
What's missing that to make it
It's simply fewer raw ingredients, less grain in there. You get less alcohol, less flavor, and less color, so less of everything.
it's diluted beer.
What is it about a nitrogen tap that makes for the more uniform denser head?
So what is it about a nitro tap that makes for a uniform, denser head? I'll let the physicists talk about the bubbles, but nitrogen forms smaller bubbles typically than CO2, right?
So I mean, it has to do with like the gas dissolve in the beer. So
And-
nitrogen is not as stable as CO2.
It doesn't stay in beer at all.
Yeah. So people don't. I mean, I don't think you can buy cans of nitrogenated beers. Not to my knowledge. You can,
Yeah, I keep one at the shop all the time because it's one of my favorite beers. It's in a nitro can.
but
Yeah.
you keep it for a very short. I mean, it doesn't stay very long.
No, they have what's called a widget in the bottom, which is at where your nitrogen is.
Ah, okay.
And when you release it, the pressure release causes the nitrogen to come out of that widget. And since it's not dissolved in the beer itself, it sort of just helps the CO2 form much smaller bubbles.
And I mean, it's going to impact like the sensation, like the bubbles are much smaller. And there's also like some discussion, but it's like not a completely settled debate on the flavor. Some people say that they taste less acidic or more acidic. And the question on how the gas is reacting and interacting with your tongue and the flavor is not a settled debate. But that's definitely, I mean, the size and the composition of the bubbles is making a difference. It's not completely clear why.
May I suggest Blake's Steaks, Philly cheesesteaks? Thank you, everybody.